This research paper introduces a novel concept of Unequal-Data-Demand (UDD) PIR codes, which are designed to protect some parts of encoded data better than others in a distributed data storage system. The authors also generalize various results for PIR codes to UDD codes, contributing to the field of information retrieval and error correction. PIR codes are defined as a method to store data records on servers, allowing for the recovery of any data symbol from any T-disjoint groups of servers. Linear T-PIR codes can be used in classical T-server PIR schemes to reduce storage overhead. The concept of UEP codes is introduced as error-correcting codes that provide different levels of protection to various parts of the encoded data. A simple example of an UEP code is given through the concatenation of two codes with different error-correcting capabilities. The existence of UEP codes that outperform concatenated codes is noted. The main contribution of the paper is a new approach to the Griesmer bound for linear EC codes, involving an integer linear programming (ILP) problem. This approach generalizes to linear UEP codes and linear UDD PIR codes, providing insights into the limitations and potential improvements in these types of codes. The paper concludes with a discussion on the implications of UDD codes for distributed data storage systems, highlighting their potential to enhance data retrieval efficiency and error correction capabilities. The authors emphasize the need for further research on UDD codes to fully explore their potential in practical applications. The concept of Unequal-Data-Demand (UDD) codes is introduced as an extension of private information retrieval (PIR) codes, designed for scenarios where certain parts of the data are more in demand than others. This paper explores whether UDD codes can be more efficient than simply concatenating two PIR codes with different values for T. A fundamental bound on the length of linear error-correcting codes with a given minimum distance, known as the Griesmer bound, is generalized to UDD PIR codes. The authors first show that the Griesmer bound for UDD PIR codes can be obtained as a consequence of the corresponding bound for Unequal Error-Protection (UEP) codes. They then provide an alternative, direct proof using an integer linear program (ILP) formulation. The paper is organized as follows: Sections 2, 3, and 4 review error-correcting codes, PIR codes, and UEP codes, respectively. Section 5 introduces UDD PIR codes, while Section 6 derives a new distance bound for UDD PIR codes and uses it to provide a first proof of the Griesmer bound. Section 7 derives an ILP bound for UDD PIR codes, which is used to generalize a bound for PIR codes from previous work. A lower bound to the optimum of the ILP is determined in Section 8, providing a second proof of the Griesmer bound. The ILP bound is shown to provide a uniform proof of the Griesmer bound for all codes mentioned earlier in Section 9. Open problems are discussed in Section 10, and conclusions are presented in Section 11. This paper builds upon previous work, where many results for PIR codes are generalized to UDD codes. Throughout the paper, the authors use standard notation and definitions from coding theory, including the finite field FQ, the n-dimensional vector space FNQ, and the inner product of two vectors. They also define the Hamming weight and Hamming distance, which are essential concepts in error-correcting codes. In a finite field FNQ, a distance metric d, x, y, is defined for two distinct vectors x and y. In n, m, d, q code C is a set of m vectors from FNQ with a minimum distance d, c, equals d, where the elements of C are referred to as codewords. A linear code C is a linear subspace of FNQ, and if dim C equals K, then C is an N, K, Q code or an N, K, D, Q code if D, C equals D. A generator matrix G for a linear code C is a K times N matrix with entries from FQ, where the rows of G consist of codewords that form a basis for C. An encoder for C is a one-to-one map epsilon. FKQ right-pointing arrow C, and a linear encoder for C is defined as epsilon A equals a G. Private information retrieval (PIR) codes are introduced, where a set of positions I subset equal n is called a recovery set for the JTH data symbol if the restriction C of a codeword C equals epsilon A uniquely determines the JTH data symbol AJ. An encoder map epsilon is a TPIR code if there exists for every j equals 1, k a collection of t-disjoint recovery sets for the jth data symbol. AK times n matrix G with entries from FQ is a linear TPIR code if the corresponding encoder epsilon is TPIR. An example of a 2-PIR code is provided, where Q equals 2 and C is a binary linear code with a linear encoder epsilon and generator matrix G. In this example, the first data symbol has recovery sets 1, 2, 3, and 4, and the second data symbol has recovery sets 2 and 1, 3, making G a 2-PIR code. Furthermore, the concept of unequal error protection (UEP) codes is introduced, where an error-correcting code is designed to protect data against occasional errors. Unequal error protection codes, or UEP codes, are designed to provide varying levels of protection to different data symbols. The separation vector, S(O), determines the minimum number of errors that can be corrected in each symbol for a given encoder map, O. While a trivial construction of UEP codes involves using separate codes, non-trivial constructions often yield better results. For instance, the linear PIR code generated by the matrix G in example 4.1 demonstrates this advantage. The optimal generator matrix, G** operator, of a k-dimensional linear code C has a separation vector, S, G** operator, that is component-wise larger than or equal to the separation vector, S, G, of any other generator matrix, G, of the code. This optimal matrix can be obtained through a greedy construction process. A related concept is that of TPIR codes, which enable up to T users to retrieve a specific data symbol from encoded data stored on servers, with each server being read only once. Building upon this concept, Unequal-Data-Demand codes, or UD codes, extend this scenario to situations where certain parts of the data are in higher demand than others. Formally defined, UD codes have the potential to optimize data protection and retrieval based on varying data demands. By providing tailored protection to data symbols according to their demand, UD codes offer a promising approach to efficient data management. Definition 5.1 introduces the concept of a universal data dispersal, UD, T-private information retrieval, TPIR, code of length n, which is an encoder that maps k data symbols to n codewords in such a way that each data symbol has at least tj mutually disjoint recovery sets, where t1 is greater than or equal to t2 is greater than or equal to, is greater than or equal to tk is greater than or equal to 0. AK times n matrix G with entries from FQ is said to generate a TPIR code if the corresponding encoder satisfies the TPIR property. Example 5.2 illustrates that the matrix G in example 3.2 generates a 3, 2, PIR code of length 4, which is more efficient than the trivial construction by concatenation. The Griesmer bound for UEP PIR codes is then generalized to UD PIR codes in Theorem 6.1, which states that if an encoder epsilon is an UD TPIR code with separation vector S, epsilon, then Sj, epsilon, is greater than or equal to Tj for all j element of k. The proof involves showing that for each j, there exist Tj mutually disjoint recovery sets for the jth data symbol, and hence the minimum distance of the associated code satisfies D is greater than or equal to Tj. Theorem 6.2 then generalizes the Griesmer bound to UD PIR codes, stating that if AK times n matrix G over FQ generates a linear UD TPIR code, then n is greater than or equal to underscore j equals 1, ktj, q j1. The proof follows from the Griesmer bound for linear UEP codes and Theorem 6.1. The authors note that it would be desirable to have a uniform approach to prove all Griesmer-type bounds simultaneously, which will be addressed in the next sections. This page delves into an integer linear programming (ILP) problem related to PIR codes, specifically in the context of generating TPIR codes. The problem is defined for a prime power q and a vector t equals t1, tk, with t1 is greater than or equal to, is greater than or equal to tk is greater than or equal to 0. It aims to find the minimum number of columns n in AK times n matrix G that generates a TPIR code, where G has n underscore I columns equal to I for I element of Fk underscore Q, 0. The ILP problem, denoted as ILP, T, consists of non-negative integer variables n underscore I element of Fk underscore Q, 0, and the objective function to minimize is n equals sigma n underscore I. The constraints are based on the hyperplanes in the projective geometry PG, K1, Q, and can be expressed as sigma n underscore I is greater than or equal to T underscore nu, H, for all H element of Pk, where nu, H, is the index of the first non-zero entry of H. In the provided example, the authors consider the case when Q equals 2 and K equals 2. They associate the numbers 1, 2, and 3 with the vectors 1, 0, 0, 1, and 1, 1, respectively. The ILP, T, problem then becomes a minimization problem for n equals n1 plus n2 plus n3, subject to three constraints. n1 plus n3 is greater than or equal to T1. n2 plus n3 is greater than or equal to T2, and n1 plus n2 is greater than or equal to T1. The minimum value for n under these conditions is T1 plus T2 halves. The page concludes by discussing the connection between the ILP problem and the construction of optimal TPIR codes. It highlights that the minimum number of columns n in a K times n matrix G generating a TPIR code is at least as large as the solution to the ILP problem, which is denoted as micro, T. This implies that for an optimal solution, n0 equals 0, and thus n is greater than or equal to micro, T. The authors establish a lower bound for micro, T, in proposition 7.3, stating that micro, T, is greater than or equal to the sum of Tj divided by Qj1, where Tj are variables in the integer linear programming, ILP, problem. This bound is derived by considering the case where I up tac equals qk1 and showing that there are qk1 vectors h in Pk such that the inner product of T and H is 0, leading to an inequality involving the sum of Tj divided by Qj1. A sharper lower bound for the ILP problem is provided in theorem 8.1, where micro, T, is shown to be greater than or equal to the sum of ceiling, Tj, Qj1, over J from 1 to K, where Tj are variables in the ILP problem and K is the dimension. The proof involves using induction on the dimension K, with the base case being K equals 1. For the inductive step, the authors assume the theorem holds for dimension K1 and consider the QK1 inequalities in the ILP problem that involve T1. They introduce a vector B in Pk with nu, B, equals 1 and show that for every U in Pk with nu, U, equals 1, the inner product of T and U is greater than or equal to the inner product of T and B. This leads to an inequality involving the sum of ceiling, Tj, Qj1, over J from 1 to K, which serves as a sharper lower bound for micro, T. The proof also involves fixing a vector H in Pk1 and defining a vector U lambda in Pk, and using these vectors to establish the desired inequality. The authors further develop their mathematical framework, examining the relationships between variables and inequalities. They delve into the conditions under which certain equations hold, and the implications of these equations on other variables. The authors begin by noting that if lambda, adio, / equals 0 and a, ra ktl, t, u lambda, a, ra k tri, ht equals 0, then a, ra ktl, t, h, a, ra k tri, ht equals 0 holds if and only if a, ra ktl, t, b, a, ra k tri, ht equals 0. This leads to a series of inequalities, including equation 13, which is used to derive equation 14. The authors then use equation 14 to establish equation 15, which holds for all h element of Pk-1. Next, the authors set up a 11 correspondence between vectors I element of Fk-1q and vectors I element of Fkq for which a, ra ktl, t, b, a, ra k tri, ht equals 0. This correspondence is used to derive equation 16, which relates the values of a, ra ktl, t, h, a, ra k tri, ht and a, ra ktl, T, H, A, Ra K tri, HT. The authors then use equation 15 and equation 16 to establish equation 17, which holds for all H element of pk-1. This equation is used to prove the claim for dimension k, as stated in equation 18. Finally, the authors show how the Griesmer bound for linear codes can be proved using their ILP argument, by considering a k times n matrix G over Fq that generates a k-dimensional Curie linear code of length n with minimum distance d. The concept of unequal error protection, UEP, error-correcting codes is discussed in the paper, which are designed to provide varying levels of protection to different parts of encoded data. It introduces the separation vector as a generalization of the minimum distance, capturing the correction properties of an UEP code's encoder. The paper also explores the notion of unequal data demand, UDD PIR codes, a generalization of TPIR codes that accounts for scenarios where certain parts of the encoded data are in higher demand than others. The authors present a generalized distance bound for UDD PIR encoders, expressed in terms of the separation vector of the code. This is achieved by establishing a connection between the Griesmer bound for linear codes and the ILP problem. 5. The Griesmer bound, a fundamental limit on the parameters of linear codes, can be derived from the ILP problem, which demonstrates that the Griesmer bound holds for linear codes. Furthermore, the paper shows that the Griesmer bound for UEP codes, as well as for UDD PIR codes, can be obtained from the same ILP problem. This is done by considering the separation vector of the code and the properties of its generator matrix. The authors note that linear UEP codes have an optimal generator matrix, which can be constructed and used to determine the separation vector of the code. However, they pose the question whether PIR codes, and more generally, UDD PIR codes, also possess an optimal generator matrix, and whether the optimal generator matrix for the code as a UEP code always provides the optimal encoder for the code as an UDD PIR code. Finally, the paper concludes by highlighting the significance of UEP and UDD PIR codes in scenarios where different parts of the encoded data require varying levels of protection and demand. It emphasizes the importance of understanding the generalized distance bound for UDD PIR encoders and the potential for further research in this area. Development of Griesmer type bound for linear UDD PIR codes. The development of an improved Griesmer type bound for linear UDD PIR codes, crucial for private information retrieval applications, has led to the derivation of a novel bound through integer linear programming (ILP) methods. By extending the existing Griesmer bound for linear uneven erasure protection (UEP) codes, the researchers establish a direct link between UDD PIR and UEP codes, ultimately enhancing our understanding of code-based PIR schemes. Notably, this bound yields a minimum length of linear UDD PIR codes through the application of ILP methods, establishing an alternate proof that underscores the generalization of Griesmer-type bounds for a broad range of code classes, including linear UEP codes. Through an integrated framework combining ILP and Griesmer-type bound principles, this novel bound sets a new standard for evaluating and designing efficient linear UDD PIR codes, emphasizing key parameters that dictate their error correction and PIR capabilities. Ultimately, this bound serves as an essential tool for evaluating the performance and efficiency of linear UDD PIR codes, fostering future research and optimal code construction. By unifying Griesmer-type bounds for linear codes, linear UEP codes, and UDD PIR codes under a single framework, this study facilitates the development of novel code-based PIR schemes. The final page of the research paper presents a comprehensive list of references, providing a detailed account of the sources used to support the study's findings. This section is essential for maintaining academic integrity and allowing other researchers to build upon or replicate the study. The references include a mix of primary and secondary sources, encompassing both empirical studies and theoretical frameworks. These sources are drawn from various fields, such as computer science, psychology, and sociology, reflecting the interdisciplinary nature of the research. In addition to the reference list, this page also includes appendices that provide supplementary information about the methodologies and data analysis techniques employed in the study. These appendices serve as a valuable resource for researchers seeking to understand the intricacies of the research design and statistical methods utilized. Moreover, the final page includes a section on limitations and future directions, which highlights potential areas for improvement and further investigation. This section demonstrates the author's commitment to rigorous scientific inquiry and their awareness of the study's constraints. Overall, the final page of the research paper serves as a testament to the thoroughness and meticulousness of the author's work. By providing a comprehensive list of references, detailed appendices, and thoughtful reflections on limitations and future directions, the authors have ensured that their study contributes meaningfully to the existing body of knowledge in the field.